Hello everyone, and we are back, and today we have the 8th talk in the what is series, and we have got Sanchayan Bhowal. He is a math first year student. He is interested in probability theory, and he will talk on what is cutoff. So over to you, Sanchayan.
Thanks, Somo, for the introduction. Okay, so before starting the talk of cutoff, so I will recall some stuff from Dipto's talk, and here it will be a follow-up of the whatever Dipto discussed, and you will see how this phenomenon occurs in Markov Chains. So let us first recall mixing time. Even before defining mixing time, you need some sort of distance because you want to estimate the distance from current probability distribution and the final probability distribution. And in order to do that, you need a certain distance in the probability measures, and that distance is given by the total variation distance. And I'll just take this to be the half of L1 now. You know there are other characterizations that Dipto and Shastra both pointed out, but I am happy to work with this characterization. And then if you have a Markov chain, so as time is going on, the Markov chain distribution is changing. And how is it changing? It's changing by the transition methods, and that is denoted by the P. So I also define this current distance at time t, which is given by max of belongs to chi. So this is the state space. That is, the Markov chain takes values on this space, and this is the state space. And we maximize among all the points in the state space, and we look at this current distribution and the final distribution, which is the stationary distribution. So what is this? So if you make the Markov chain run for some time, after time t, if you start at, let's say, point x, fix point x, and you start at x and make the Markov chain run, and at tth time, I say the Markov chain will have this distribution. And so what is this transition matrix? Transition matrix basically shows that the probability of jumping from one state to another state. So at tth time it will be p to the power t and x comma dot. This dot shows that at each point it gives the distribution. And what is this pi? This pi is basically the right eigenvector, left eigenvector, and this is basically means that if you start with this stationary distribution, you will remain at the stationary distribution for forever. And unfortunately, this pi is not unique for all Markov chains, but for some Markov chains, it's unique. And those Markov chains are the irreducible Markov chains. This notion comes from basically the connectivity. So if you imagine a random walk in a graph, that is, you have a graph and you are randomly choosing one of the vertices and moving on. And so if the graph is connected, we say that random walk is irreducible. And you sort of generalize this in Markov chains and you get irreducible Markov chains. And there is another notion that is called the aperiodic. What happens in aperiodic is, for example, if you take a bipartite graph, let's say, so here are a few points, and you are doing a random walk. So what does a random walk mean? You start from one point, you randomly choose from this 2 points, let's say this, and you come here. And again, you have, let's say, more edge here, and then you randomly choose from one of the neighbors and go back to that point, and you continue this. So one thing you can always say, that at odd step you will always be here, and at even step you will always be here. So basically you will kind of oscillate between the odd and even partitions, and that's something you don't want, because this oscillation will cause problem with the convergence. That is why you need a period. That is, there does not exist such partitions. And this kind of Markov chain, once you have this condition, you can say that dt is in fact less than equal to C. That is dt goes to. So, however, we are not happy with this. Because once we have convergence statements, we always ask for the rate. So what is the rate? And this alpha basically denotes the rate. Now we want to know what is the rate. In order to make sense of rate, we define what is called mixing rate. a single region, we define T mix to be T mix of one. Fair enough, we have mixing time now, and this measures the rate of the chain. Now let us go back to the one of the examples that Victor pointed out, random walking hack. So what is a hypercube? A hypercube is a graph, and the vertex is this set 0, 1 to the power n. That is basically n tuples containing 0 and 1. And what is the edge set? Edge set is all those points such that the one norm is 1. That is, they basically differ by 1 point. And that is the edge. For 3 dimensions, it will look like a cube. And just like any other random walking hypercube, but any other random walking graph, what you do, you start from some point, you randomly pick one of the points, let's say you pick this, and then you again randomly pick, and you continue this. However, there is a problem. The problem is about this aperiod. This hypercube graph is bipartite. So again it causes a problem of periodicity. However, if you have a periodic chain, it's very easy to make it aperiodic. So what you do is you introduce a laziness. With some probability you say that, okay, with some probability I will stay here itself. And I will not move. And then I will choose, with other half of probability, you will choose randomly from the other point. And you move. So what this happens? If this happens, then what will happen? Even if you have a bipartite graph, let's say, then you can't just say that at odd step it will always be here, because there is a probability of remaining here itself. So at even step also it can be here, and that removes the periodicity condition, and this chain becomes aperiodic. So what you are basically doing is, if you take the transition matrix, you add I to it and divide by 2. This division by 2 will, like in the diagonals, you will get half now. So there is a probability of staying there itself, and that will make the chain aperiodic. Fine. So now you have a random walking graph. Now you are interested in the mixing time. So as you guys have already seen, some bounds on mixing time. Unfortunately, none of them are tight enough. So I will state the bound for random walking hypercube, that is half an log n. Now let us critically understand what does this mean. So in order to understand, let us first draw this graph. This is the x-axis and this is t. So in the beginning, you are starting from some point. So the distance from the stationary is quite high. Okay. So one important thing, the stationary distribution is uniform here. Why? Because the graph is regular. Like from here, there is three. For if you just look at the three-dimensional case. So here you have three vertices, three adjacent edges. From here also you have three adjacent edges. The degree is same for all the columns and the vertices. And for n-dimensional, it will be n regular. Fine. So in the beginning, the distance from the station is quite high. So you will meet here for certain time. And then I say that it will have a sudden drop at some point. Why is that? Let's see. So let us look at T mix 1 minus epsilon and T mix epsilon. These are 2 points in the time axis. Now you can see that these two T mix and T mix 1 minus epsilon, the relative order, if you divide T mix epsilon by T mix 1 minus epsilon, then it goes to 1, because there is a half n log n and half n log n, that will if you divide it, it will go to 1. Basically, you are saying that relatively they are coming close. So what is happening is, this graph is even becoming more abrupt, the fall is more sharper, and ultimately it's tending to something like this. So this kind of phenomena, where you have an abrupt change in the dt graph, you call it cutoff. So let us rigorously define this. But now you will ask, what does this end show? Remember, in a hypercube, you don't just have one graph. You have a family of graphs, which depends on n, and you are making this n grow. So here also we need to take a Markov chain, not just one Markov chain, but rather a family of Markov chains. So then you will get, for each of this Markov chain, you will get a T-mix. So it will depend on n. Similarly, T-mix 1 minus epsilon will also be dependent. Now as you make this dimension grow, it should go to 1. So relatively they should come close to each other. And there are the equivalent conditions for this. This is also very easy from the, like, where is this dt graph going? Just say that this should be go to this state function. And it's not very hard to see that these two are equal. Fine. Now we have seen one example of cutoff where like the example of random walking hypercube where this kind of phenomenon is observed. Now let us come to shuffling. So why do you need shuffling? Let's say you are playing a game, but now you want to pick one card at random. So what do you mean by that? You want to pick uniformly one among the 10. So the main point of shuffling is you should make it as random as possible, so that you can uniformly pick one card. So you want to sample from a uniform distribution. So what you do is shuffle the card. And how do you shuffle? There are many ways of shuffle. So one famous way is this top to random shuffle. So what you do is pick one card from the top, and you put it at a random place, and you continue like this. Yeah, you might feel that this is a very bad way of shuffling, but this is one of the primitive examples where mathematicians start to understand something. This is called the top to random shuffle. What is happening in this circle? So you have SL, the symmetric group of n cards. So basically you have permutations of n, and you are jumping from one permutation to another permutation. So again you are creating a Markov chain out of it. Now as you have a Markov chain, it goes to the stationary distribution because this will also be usable in the quadratic. So then the stationary distribution turns out to be uniform. So now we are in a good scenario. So if you do this Markov chain for a long time, you will get a uniform distribution, and if you pick one card at random from the top, let's say you will get some uniform distribution. You can uniformly sample from one from the. So that is good enough. Now we will ask what is the mixing time of this for n cards. The mixing time turns out to be n log n and n log n. Again, the proof of this comes, the lower bound is very simple enough. You just need to write this total variation distance in the other characterization that Victor pointed out. And the upper bound comes from something like you need to observe some event and then bound it with the coupon collector time. And as Shashwata has already said, the coupon collector time is something like this, so you get this upper bound. Okay. Now this is the primitive way of shuffling, and if you actually do this for 52, this turns out to be around 205, and of course you won't do before a game, you won't do a 205 shuffle. So now the famous way of shuffle that is now commonly being used in casinos or before games also, that is the riffle shuffle. Okay, I think most of you guys know how to do riffle shuffle, but I'll just try this stunt also. Although I just learned it before the lecture, I don't know if I will be successful. So if I am not, please forgive me. So what you do is you take these cards and divide it into two parts, and you put the cards like this. Now, once you do this, what happens is, basically if you carefully observe this, some cards from the first deck has fallen here, then some cards from the second deck has fallen here, and this has been done. Like as you can see, yeah, I think I didn't mix it up. So some cards from the first deck are here, and some cards from the second deck are here. So there has been some sort of reorder. Now if you do this for long enough, and then again you can ask the same question, what is the mixing error? The mixing error turns out to be very small. In fact, it is of like 2 log. That is very good. Now if you compute this for n equals to 52, this turns out to be around 7.6. Now this was the famous paper by Aldous and Pak on shuffling cards and stuff. The proof is a little bit involved because it uses some representation theory. Anyway, so once this they discovered this kind of phenomena, it was a huge thing because now you have a very at small time you can do a you can reach the stationary distribution very fast. And after a few months only, the New York Times, this came up as an article by Colata that 7 shuffles are enough. But you can just look into New York Times article about these 7 shuffles are enough. It's very nice article. So as you might know, the famous story of Pak is that he left high school in the very early years and he went on to do magic. But later he came to Harvard to do PhD in mathematics and he did the rest of the magic in math. So anyway, so this is all about shuffling. So, now let us come to see why is proving cutoff hard. The first thing is that if you look at the mixing time of Hypercube carefully, you will see that you don't only need bounds on upper and lower, but also you need the constants to be matched, and that can be hard to do. So what mathematicians were thinking is how to characterize the cutoff phenomenon. And the problem is there is no general characterization known yet. So, however, there are some necessary conditions that is required. Let us come to some necessary conditions. Before going to the actual necessary condition, let us define some sort of relaxation of cutoff that is called pre-cutoff. And what is pre-cutoff? So we define it for draw the picture. So instead, in the earlier terms, in the earlier definition of cutoff, what I did is I said that this should be of the same order. However, now I am saying okay, I am relaxing it, and I am saying okay, I don't need exactly 1, but I can say it's bounded. So over the supremum of 0 to half. And this half is for some technical reasons because you will see for after half it's useless to say bounded because this will be some 1 or something. Anyway. So this is called pre-cutoff. Now we will give a necessary condition for pre-cutoff, and that will also be a necessary condition for cutoff. Why? Because cutoff, of course, implies pre-cutoff. So let us come to the have a an algorithm chain. Algorithm basically means irreducible and empirical. Then if we have this condition, sorry, I wrote out this one. If xt then has p cutoff, then in fact, the proof is very simple. If you just recall one of the upper bounds by given by T-real aggregates, and let me just recall it from this lecture. So it just says that let us come to the proof, and it's very simple. So assume that it doesn't happen. So basically then you will get a subsequent. Like assume that this condition doesn't work. This is bounded by some constants. Now you use this lower bound. So if you use the lower bound, then you get this. You basically need this. And since you have this, since you have this subsequence, which is this kind of series, and then you can say C times Markov Convergence. Now, of course, this is not bounded, because if you take the supremum over 0 to epsilon, basically if you make epsilon goes to 0, then you will see that this will go to infinity, and hence that will be a contradiction to p cutoff, because they assume the chain has p cutoff, and hence you have this necessary condition that T-real n minus 1 by T-real should go to 0. Fine. But this is a necessary condition. Is this sufficient? So Perez, when this condition was given, Perez conjectured that this is sufficient. Unfortunately, it's not. So there's a famous example by Aldous, and now we'll look into that example. So it basically defines a graph and performs a random of money. So how does it do that? It takes a long graph, a, and then he introduces these two paths. And the length of this path is 2n. The length of this path is n. And this length is 5. And you say that it jumps from here to here with a probability 1/3, and from here to here with a probability 2. Basically, it means at each position you are doing a coin toss, and which has a high probability of giving heads as 1/3 and probability of giving tails as 2/3, and if head comes, you move to the left, and if tail comes, then you move to the right. Right? And you similarly do that here also. 1 by 3. However, you change the speed over here. What you do is you make this 1 by 4, 7/5, and 4 by 5. And now you move on this. Now you perform the random up on this graph. Okay. Now, if you look at this graph, you will see that if you start from any point, there is a high probability of shifting here, coming here, because the drift is towards this side. So I will give an intuitive explanation to all this. I won't go into the rigorous proof. So bear with me. So you will see that the concentration of the whole probability is towards this. So what is the stationary distribution? The stationary distribution will be concentrated at this point. So you will say that when you start from any point and you come here and you use this point, you can say that okay, the chain has mixed. So basically we need to estimate this time of hitting this point. Okay. Let us look at how this time is. Let us draw a graph. Again, in the beginning, if the point let's say starts here, so it's very far from the other point and the distance is quite. Now, after approximately 15 n steps, because the drift is around 1 by 3 here, towards this side, and approximately after 15 n steps, you reach here. This is 15. Is it visible? The approximately at 15 steps you have reached here, but you are still quite far, so distance is fine. Now, how many number of steps you should take to reach? It's around so 5 by 3. And how many steps you should take here? It's 6. Fine. Now let's say you chose this path, and you choose this path with certain probability, and you choose this path, and you reach this point at 5 by 3. However, you are not always taking this path, right? You have a probability of taking that path. So if you take this path, the probability, the distance will decrease by some amount, but it won't decrease a lot. So you can say that around 50 n plus 5 by 3 n. It has decreased by some. But it will happen that sometimes you will take that path, so it will decrease to the very close to 0. It will remain here for some time. However, after 6 n step, that is 15 n plus 6 n, that is 21 n. At 21 n, you will always say that okay, I have with high probability I have reached here. So this basically means that you have reached. So yeah, now the distance from the station will be very less. And you will you will find something, graph something like this. But now you cannot say that this has cut. So that is the problem. However, this will have pre-cut. Why? Because you will see that these two relative, it's 21 by around 15 n, which is bounded by infinity. So although there is no cutoff, but there is pre-cut. But what is this theorem say? If you have pre-cutoff, then this will do this condition. So let us say this condition star. So in this example, star holds what cutoff is.
So my question may be a bit of a technical question. Do we need to take n odd because otherwise this chain is has period 2? Or we just change one of them to say 2n plus 1 or something? I think this will be.
It's periodic.
Why?
What is it? Periodic.
If n is even, then it's period.
Oh.
So then it has a period 2.
Why is it?
I think so because in the split in the cycle there are 3n many.
No, but there is this. You are giving two different probabilities.
Yeah, but you can't return to the same point.
Look at the end vertex. You can't return this.
Yeah.
You can't.
Anyway, I don't think
It is
it
not
matters a
period.
lot.
Yeah, it matters a lot because then you will take the
Yeah.
some family will be you take
And
out
anyway,
the-
you can just change that 2n to 2n plus 1. That then.
No, it's fine. If you make n odd, then even if 2n is even, it's fine.
Yeah, you get another family.
Yeah.
No, anyway, look at the last vertex. You can't go back there.
No, last vertex there are edges backwards also. You want the
Yeah.
chain to be induced.
This is this.
This is it. How can you?
Otherwise, it's not. Yeah, probably. I'm not exactly sure that anyway is a problem, but I think anyway it's fine because even if you take n odd, you just need a family. Fine. Now all these were some negative examples where cutoff is not happening. So is there any characterization of cutoff in some good enough convergence? So what was the problem in this graph? The main problem in this graph was that you have two paths and each of these paths have different speeds. So now what if you do a random walk in a graph which does not even have two paths? Basically you are taking a tree. For those trees you can actually say that this condition is sufficient, and in fact this was proved in a paper.
I think this is not visible.
They prove that star is sufficient.
Sanchayan, it is.
I think it's better to use a plus.
Oh,
This is not visible.
yeah. But they show that star is sufficient, this condition is sufficient for that. Wait. In fact, they give a general characterization also, but they say that they define something called worst states, and if you have the hitting time of those worst states, you can actually give another characterization of that. What are the other positive results? Another positive result is given by Ding-Rubinstein test, where they prove that this start condition. I don't exactly remember the year. Star is sufficient for vertex. Vertex chains are like some kind of, you can imagine as a population evolving in a time. Like there is some a number of population and it's giving birth to some more, and or it's giving birth to some of the population is dying, or it's remaining at the same place. So you kind of have a Markov chain evolving in time, and then you can ask again the same question of mixing time, and you can definitely ask the same question for cutoff. And what they prove is that this star is sufficient for convergence. Okay, I think I started already. That's it, more or less. Yeah, I can get a reference.
I guess the tmx should be something fold order, not two.
This is
Yeah.
fold order? No, I don't think.
Because it comes out to 3 actually. If you put n.
N equals 15.
Yeah, it comes out 3.
But anyway, it won't give the exact
No,
value. This is exact.
I just now calculated it.
But anyway, it doesn't matter. There is a
Yeah, yeah.
plus CN also, right? So
Plus C, no, there
plus
is no
C.
This is
This is assembly.
the window is whatever.
Oh, order.
Yeah, order.
Yeah, it's 2 log. 2 login comes out to be 7.1. I think you are using some different base. You should use the E base. Anyway, it's fine. ln. Yeah. Anyway, so if you look at the, I'll give the
I
references.
think we just have to account for that extra constant. That extra constant will give the value to be calculated.
I don't think the extra constant matters.
No,
No, extra
you are
constant.
putting in n equal to 52 and finding the value, right?
Yeah.
So for that maybe that increases the value just enough to get.
No. It's around 7. In fact, you can do better. Like there are some newer methods like GS or Shuffle where you can actually drop these 2 also. You can get 4. Even in 4 shuffles, you will get. So I'll just give the reference. The first is the book by Devin Perez and Newman. And the second and third are 2 lecture notes. One is by Justin Salas. There is another lecture notes by Andreas Sticky. So hopefully the spelling is correct. And Justin Salas goes, the lecture notes goes into much deeper theory than Markov Chains and explain. They use some modern methods of variation. Anyway, so yeah, this is for general reading and this is very concise. So if you are already know a lot about this, then this is very good.
So are there any questions? If not, let's thank our speaker once again and I think it's a good time for the director to say cut.